Okay, in the previous video we reached to this point, the total number of electron in the conduction band, which is given by this relation. We started from this relation that the total the number of electron in an energy range E and E plus D is given by this two factors. The first one is the total number of available states, and the second factor is the probability of finding the electron in that energy level or in that available states. Now to calculate the total number of electron, we will integrate this equation and we get the total number of electron in the conduction band, which we did here, and we call it equation number 2, and we consider the limit of the integration from EC to infinity, because the bottom of the conduction band is represented by EC and the top of the conduction band is represented by infinity. If electron jumps from valence band to conduction band, then they can occupy any place from EC to infinity. That's why the integration limit is from EC to infinity. Now this density of state G of E is given by this relation. Here H is the Planck's constant, and this ME steric is the effective mass of electron, effective mass of electron. And the Fermi Dirac distribution function is given by this relation. Here EF is the Fermi energy, which in the case of intrinsic semiconductor is in the middle of conduction band and valence band. This is EF, the Fermi energy. Now we use the approximation, and the approximation is given by this. We suppose that the difference of E minus EF is very much greater than the product of K and T, where K is the Boltzmann constant. Then E minus EF, if we bring this factor here, will be much greater than 1. If we take the exponential of both sides, or the exponential of this factor will be much greater than 1. Now if we add this factor with 1 plus exponential of this factor, this will be approximately equal to exponential of E minus EF over KT, because this is much greater than 1. So if we add 1, then it doesn't matter, that doesn't change this factor too much. So the Fermi Dirac distribution function now will be equal to 1 over this factor, E minus EF over KT, but if we bring it to the numerator, then it will become EF minus E over KT. Now using equation 3, which is this one, and equation 4, which is this one, and equation 2, in this equation we get this expression. Now here we will use some supposition, and the first supposition is let E minus EC over KT is equal to X. If we differentiate, then D will be equal to KT over KT times dx, because EC is constant, so it's the differential will be on this DE. This factor will be 0. du over KT is equal to dx, then D is equal to KT times dx. Now if energy changes from EC to infinity, like if energy is equal to EC, this implies if you put E is equal to EC in this factor, then X will be equal to 0. If energy is equal to infinity, this limit, this implies that X should be infinity. So the total number of electron in the conduction band will be equal to pi divided by, I will use some other supposition also. I will modify this factor. Here the factor is E minus EF F over KT, E minus EF over KT. is equal to E minus EF. I will add EC and I will subtract EC divided by KT. Now from this I will get E plus EC over KT plus EC minus EF over KT times, if we bring these supposition in the above equation, then our final expression will be n is equal to pi by 2 8 me steric divided by h square whole 3 by 2, and the limits are now from 0 to infinity, and we have this KT factor which is 1 over 2, and we have x whole 1 over 2, and we have e raised to the power minus x, and we have e raised to the power minus EC minus EF over KT times dx times KT into dx, because dE is equal to KT times dx. So do it by yourself, it's very easy. Now these factors, this is constant now, and this factor is constant, this factor is constant. If we bring this factor outside of the integral, then our final expression will be equal to n is equal to pi by 2, and then we have 8 me steric divided by KT whole divided by h square 3 by 2, and we have KT whole 3 by 2, and we have e raised to the power minus EC minus EF over KT, and then we have integral x whole 1 over 2 e raised to the power minus x, and we have dx. Now the integral here is a gamma function which can be written as, like this integral is again a gamma function which can be written as from 0 to infinity. Okay, 0 to infinity x whole 1 over 2 e raised to the power minus x dx, which can be written as 0 to infinity e raised to the power 3 by 2 minus 1 e raised to the power minus x dx, which will be equal to the integral of, which will be equal to gamma function with 3 by 2. If we calculate this, we get the pi square root pi divided by 2 from this integral, which you did in your mathematical method course. So if we put this in the above expression, then n will be equal to pi by 2, and we have 8 me steric divided by h square whole 3 by 2, and we have KT whole 3 by 2, and then we have e raised to the power minus E C minus EF over KT times pi by 2. If we rearrange all this factor, we finally get 1 over 4. 2 is here, 2 is here, so it's 1 over 4. Pi 1 over 2 into pi 1, which is pi 3 by 2. Pi raised to about 3 by 2, and then KT whole 3 by 2, and we have 3 by 2 here. So it will be equal to 8 pi me steric KT divided by h square whole 3 by 2, and we have e raised to the power minus EC minus EF over KT. The final expression will be equal to 2 times n is equal to 2 times 8 pi me steric over into KT over h whole square whole 3 by 2, and then we have e raised to the power EF minus EC over KT. I can write this to be equal to Nc times e raised to power EF minus EC over kT, where Nc is equal to 2 times, this is 2, sorry, yeah, this is 2 pi me steric kT over h square whole 3 by 2, and is called the effective density of state, and is called the effective density of states. So this factor n is equal to Nc times e raised to power EF minus EC over kT. Here we have the number of electrons per unit volume. Here this factor will give the effective density of state, and this exponential factor basically gives the probability of filling all this state. Probability of filling all this state. So this whole factor will give us the total number of electrons in conduction band. Now we have three expressions which are listed here. The first one is G of E, which is basically the density of state, and its value is pi by 2 at me steric divided by h square whole 3 by 2, and then we have E minus EC whole 1 over 2. If we plot this factor as a function of energy, this is G of E, and here on this side we have energy, and suppose this is the bottom of conduction band EC. If we plot it, we get a function like this, a graph like this, which is proportional to this factor, because all these quantities are constant. The only variable quantity is this one, so it's proportional to E minus EC whole 1 over 2. Now the second factor is f of E, which is given by 1 over 1 plus exponential of E minus EF over kT. If we plot it, we get a factor like this. Here we have the bottom of the conduction band, and it will give a function like this, the Fermi-Dirac distribution function, like this. Now the total number of electron will be equal to, which is n, which is equal to G of E dE into f of E. If we plot it together, we get a function like this. So this will give us the number of electron in the conduction band. So this is all about the intrinsic carrier concentration, or the number of electron in the conduction band, or the electron density. And this is the graph of different factors, like the density of states given by this plot, The Fermi-Dirac distribution function is given by this plot, f of E, and this side we have energy. On this side we have N, and this side we have the energy E. And this will give us the total number of electron in the energy range E and E plus D. The energy range is E to E plus D. In the next video, we will move, I think, to the concentration of hole in the valence band. Thank you.